use it to keep track of time. But this is a slightly different pendulum I've got here. It's called a double pendulum, so it's got two pieces of metal jointed together a little bit like a leg. So the geometry, mathematics of this is very simple to describe these two pieces of metal. The physics which controls how this will fall is also not that complicated, but being able to use that to predict the behavior of this thing is almost impossible. Whoa! Oh, look at that. And I think the fact that you're laughing is a perfect example of the fact that this is unpredictable. Laughter is a response to, whoa, I wasn't expecting that to happen. But the real challenge of chaos theory that Poincare raised is, okay, that was very complex behavior, but can I repeat the exact same behavior? And actually, I have a little notch here, and I try and start the pendulum off in exactly the same place. So let's see whether, if you can remember what it did before, is it going to do... Whoa! That's already doing something completely different. I mean, it's still quite funky, but okay. And then it seems to. This is my favourite desktop toy. I can play with this for absolutely hours. So if you'll indulge me, I'm just going to do one more because it's just a. Whoa! Oh! Whoa! I mean, where did that come from? Unbelievable! Whoa! Give it a round of applause. That's a. Oh. So this is the challenge of chaos theory, is actually just very complex behavior, but being able to repeat that behavior. So I've got another desk which I have on my desk at home. It's again a pendulum, but it's got 6 magnets which attract the pendulum, and over each magnet is actually an answer to a question. So I use this to make all my decisions in life, actually. So you can ask it a question. So for example, should I make a bet on Arsenal beating Swansea on Saturday? So we're just going to set this thing going. So the answers are like, try again, no way, definitely, maybe, yes, ask a friend. So here's a little one we did in the lab. So this is an example of this pendulum. I've got just 3 magnets here, but you try and predict which magnet the pendulum is going to end up at. You know, it's wobble between them all. Is it going to end up at the top one, and then right at the last it ends up at the bottom one? But it seems incredibly. So here we go. Maybe. Well, that's not good enough. Actually, the challenge. I mean, this is a bit like an asteroid flying round, and the magnets are like planets, and you've got to try and decide, well, which planet is going to get wiped out by this asteroid. And in fact, Poincare discovered this chaos theory when he was trying to understand the solar system, to see whether the solar system was stable or not. And what he says, definitely, great, yes, always right. And he understood that even the solar system, trying to predict whether that is stable or not, is incredibly sensitive to just very small changes in where the asteroid is. So here's 3 computer models that I did of where the pendulum is going to end up. So I've coloured those 3 magnets, yellow, red and blue. And I've started the pendulum off in the top left-hand corner. The first experiment, the thing wiped out the blue planet, but then I changed the 6th decimal place of one of the coordinates of the starting position. So you can't even see that it's changed, but when I then ran the model, well, it sort of followed the same path for a while and then completely veered off and did something completely different. That time it wiped out the red planet. Then I changed the 6th decimal place again. Again, it's similar sort of trajectory to start with, and then wipes out the yellow planet. So that very small change causes a massive difference in the outcome. So this is incredibly difficult to predict, even though I have the equations and I might have very accurate knowledge about the starting position. Unless I have complete knowledge, I really cannot know what the answer is going to be. And this computer graphic helps you to try and make a prediction about where the pendulum will end up. So if I start the pendulum over a yellow region, that means that the pendulum is going to end up at the yellow magnet. So you can see there are some regions which aren't knowable. I mean, so the yellow magnet is sitting under that big yellow blob there, and sure enough, I start the pendulum next to the yellow magnet, magnets, and the other two can't pull it, and so it's just going to wobble and then settle on the yellow magnet. There's another area sort of opposite the yellow magnet, which if I start it there, it's again quite predictable. A little error won't cause it to do anything terribly different. It will just swing backwards and forwards, and eventually the other two magnets can't pull it either side. It ends up again at the yellow magnet. But I started my pendulum in the top left-hand corner, and this is an example of something called a fractal. So a fractal are these mathematical geometric shapes which have infinite complexity. So as I zoom in on this area, it never simplifies. It never suddenly becomes, oh, now it's all yellow. So I know that if I've got if I've got the accuracy up to this point, I know it's going to hit the yellow magnet. It just keeps on being yellow, blue, red, yellow, blue, red. As I zoom in, I try and get more and more accurate. Still, the 50th decimal place can tip it over from being yellow to blue. So this is a region which says, if you're here, you really cannot know what is going to happen next, because you've got that infinite sensitivity to just a very small change, something we call the butterfly effect. Now, of course, the trouble is this chaotic dynamics affects so many things we would like to know about the future. The weather, for example, the solar system, even population dynamics. And so actually I took with me on my journey to the edge, each of these edges, an expert in this area, somebody who's been at this edge trying to push it ever further. So the expert I took actually on my journey to try and predict the future was a colleague of mine in Oxford, Bob May, who's a mathematical biologist, and he was one of the people who understood that population dynamics, very simple sort of feedback equation which controls the population of animals from one season to another, can also have this incredible sensitivity to small changes. So I went to go and talk to him about his ideas. Actually, he's now Lord May. I shouldn't call him Bob May. Lord May. He's a cross-party member of the House of Lords. And he's actually working with Andrew Haldane at the Bank of England, and trying to look now not at population dynamics, but at the economy, to see whether the economy, the equations for the economy, it's just data and numbers and kind of rules which control how those numbers will evolve. They're trying to see whether the banking crisis of 2008 might have been a result of very sort of chaotic motion that would have been very hard to predict. So he's actually working with governments, trying to explain to them the limitations of being able to know what's going to happen next, even if you know that how the theory which controls it. And I went and had lunch with him at the House of Lords, and he made this statement to me whilst we were having lunch. He said, not only in research, but in the everyday world of politics and economics, we would be better off if more people realised that simple systems do not necessarily possess simple dynamic properties. So I asked him how he was getting on trying to explain some mathematics of chaos theory to the MPs at Westminster, and he said, no, Marcus, they're mostly interested in their egos here, not in mathematics. But then I came back to this dice, and I was intrigued. Well, is the reason that I can't know this dice because the dynamics are chaotic? And I got a little bit of surprise. I discovered a piece of research that had been done just recently by some Polish mathematicians, who they've used high-speed cameras to record what it is doing as it hits the table and rolls. And they've actually understood that in uncertain circumstances, this is much more knowable than you might think. So actually, I coloured the faces of the dice different colours, and we're going to draw some similar pictures to the one for predicting where the pendulum is going to go, which will help us to know what arrangement of the dice do I need to make it land, say, on the red side or the blue side. So here are the pictures that the Polish team created. And the interesting one is the top left-hand picture, because in this picture, the colours are not fractal. It's a very clear sort of a signal about where this thing is going to land. So what this is measuring on the two axes is, on one axis is the height above the table, and the other one is the angle at which you launch the dice from your hand. And because this picture isn't fractal, it means that actually a small change isn't going to alter the side that it's going to fall on. So what the table that's being described in this particular picture is a craps table particle which actually is quite soft, and the dice dissipates a lot of energy when it hits the table. So it's kind of like a bit of an old squidgy craps table. So, you know, perhaps a casino that's had seen better days. So this is the one that you should go after, because it turns out that actually if the dice is losing a lot of energy as it hits the table, if it's a soft table, then actually this thing is quite predictable. And so if you take one thing away from this talk and my book, it's the following, okay? That more often than not, there's a higher probability that when you play on such a table, that when you release the dice, it will actually land on the face, which is down on the palm of your hand when you release it. I wonder what... Well, let's take this. Let's make a soft craps table. Oh gosh, yes, no, I forgot how, but we'll try and I'm trying to get dressed in a bit. So let's make this kind of soft, and let's see whether we can make this work. All right. So okay. So I'm going to have 6 on the bottom. So I'm going to try and get a 6. So I'm going to let this fall. Oh, it's a 1. Oh. That's a bit rough. That's why I chose maths, you know, to prove, to make sure these things work. But actually, you know, of course, it's a probabilistic thing, so more than likely, so 1 in 6 times that works. But as the table gets more and more rigid, so the table I got here is a very rigid table, and it bounces a lot. This is described by pictures which are becoming more and more fractal. So it says on this table, again, a very small change, that butterfly effect, we call it, a very small change can cause it to go from the 4 to the 6 to the 1, and again, it says that you cannot know what this dice is going to do next. Now, that edge is actually under very classical kind of 19th century ideas of science, but of course in the 20th century we realised that maybe the universe isn't as predictable and deterministic as Newton actually thought. And so the next edge I'm going to take you to is the edge which we discovered at the beginning of the 20th century, that maybe actually unknowability is actually at the heart of the way we must do science. And this is the science of quantum physics. So quantum physics almost has embedded in it the fact that you cannot know. And so the object I took with me on my journey to the edge of the quantum was this pot of uranium, which I bought on the internet. It's amazing what you can buy on the internet these days. So the interesting thing about this pot of uranium is that on the side, it tells me the activity. So it tells me that there are per minute, on average, there are 984 bits of radiation being kicked off. I probably shouldn't do that. There are 984 bits of radiation being kicked off this uranium per minute. But that's on average, and what this pot can't tell me, and in fact what physics at the moment cannot tell us, cannot know, is when it's going to do that. There is no mechanism currently known, and it's believed that there is no mechanism, it's a fundamental part of the way we do physics, that there is no mechanism which will tell me when the radiation is going to get kicked off. Okay, on average 984, but when is it going to do it? It seems to be totally random, and we don't seem to be able to know. And this is at the heart of something you've probably heard of, Heisenberg's uncertainty principle. Heisenberg's uncertainty principle kind of articulates the fact that we cannot know certain things. Heisenberg's uncertainty principle says that, for example, if I want to know where an I'm trying to describe an electron, and if I'm trying to do Newtonian physics, I need to know where the electron is and how it's moving, so I need to know its momentum. But Heisenberg's uncertainty principle says, well, actually, you can't know both of those things simultaneously. That the more you know about where the electron is, the less you can know about how it's moving. So this is actually, it's not a wishy-washy statement, it's a very precise mathematical formula. It actually comes out of the mathematics. And the formula I've written here is that the delta x is the error. So getting smaller and smaller, I know more and more about where that electron is. To make this equation work, the error in the momentum, it means the momentum can suddenly have more, kind of whole to different possible values. And if I get to know, so you might say, oh, I know where the electron is now, so now I'm going to measure its momentum. Well, as you get to know more about how that thing's moving, you suddenly lose knowledge again. Suddenly the electron could be anywhere, as the error gets larger and larger. So if you indulge me, my favourite physics joke is about Heisenberg. So Heisenberg is bombing down the motorway in his BMW, and the police pull him over. The policeman gets Heisenberg out of the car and says to him, "Sir, do you know how fast you were going?" And Heisenberg says, "No, but I know exactly where I was." Good, yeah, you're a good audience, you see. Anyone who's sort of sitting there saying, "Why were they laughing? That wasn't funny." You shouldn't have to explain a joke, I know, but the point is, you know, because he knew exactly where he was, it meant there was an uncertainty about the different values that his speed could have been. So it could have been a whole range of different values. So here's the follow-up to the joke. The police officer says, "You were going 200 kilometers per hour." And Heisenberg goes, "God, now we're lost." Now, we're getting that one, yes, exactly. So, because we now know how fast he was going, he's lost information about his position. There's a third bit to the joke. You can ask me the questions, the follow-up to that one. But Schrodinger happens to be at the back of the car, so... we'll go. But actually, physics has a different interpretation about this. It actually says, well, maybe it's kind of our language which is wrong, that actually this electron doesn't have position and a momentum at the same time. That's a very sort of old Newtonian classical way of thinking about it. Actually, we should think that this thing doesn't have a position until we observe it. So actually, we have this thing with a quantum wave function. So this kind of, it tells you the likelihood of finding where the electron is, but it actually isn't there. It doesn't have position until you make the commitment of observing it, and then it collapses into a position. The wave, so if the wave is high, it says you're more likely to find it here. So it says, no, you're very unlikely, but there is a chance that you'll find it there. Now, I find this totally unsatisfactory. It's because, you know, my feeling is that you do an experiment. If you set it up the same way, you're going to get the same answer each time. This says, no, you're just not going to know. You can set up the same experiment, do it over and over again, and each time you do it, the electron can do something completely different. So there's no determinism here, no mechanism which is going to say when this thing is where it's going to be. And actually, this control... it's the same sort of mechanism which is at the heart of explaining the radiation of this uranium. So actually, I know quite a lot about the momentum of the particles inside the nucleus of the uranium, which means I know very less about the position. The position can be on a whole range of possibilities, and when we observe it, sometimes that position can be, most of the times it's still inside, but sometimes it can be outside, this thing called tunneling, and then it radiates. So this kind of undeterminacy is actually at the heart of explaining the radiation. But I just cannot believe there isn't something that we haven't found yet, something that will tell us when it's going to do that. I mean, is it genuinely something that we cannot know? Or is it just that physicists have given up and it's, you know, this theory works very well, so why do we need to bother? Because it tells us everything we need to know. And I'm not alone in thinking that surely this is actually not genuinely something we don't know, it's just that we haven't had the revolution which will give us the mechanism. And was certainly a believer in this being not the final answer. He wrote very famously, quantum mechanics is very impressive, but an inner voice tells me that it is the real thing. The theory produces a good deal, but it hardly brings us closer to the secret of the old one. I am at all events convinced that he does not play dice. And it's certainly true that theory is probably one of the most well-tested theories that we have on the scientific books. You know, to use this theory of probability in quantum physics, it's good enough for nearly everything you want to do. But surely there's something going on, you know, inside this uranium which is controlling when it's going to radiate. No, of course, that this mechanism, if it exists, is a very weird one. The idea of entanglement has made us understand that it won't be kind of localized inside the uranium. It will be something which actually spans the whole universe, which is controlling the decision about when this is going to radiate or not. But it is a mechanism. Maybe there isn't, and maybe this is genuinely something we cannot know. Now, I said that I was going to kind of tease out a little bit of the unknown for the idea of religion and God, and so I'm interested to talk to some scientists who are actually religious and see, you know, what their how did they marry up their ideas of doing science and religion. And the person I took on my journey to the edge of the quantum world is actually an interesting scientist. It's John Polkinghorne. John Polkinghorne, the quantum physicist, trained with the best, trained with Feynman, Dirac, can't ask for better teacher than those two, but then halfway through his career he decided he wanted to be ordained as a priest in the Church of England. He kind of refers to himself as a kind of like a vegetarian butcher. But I was quite interested because, you know, for me, actually it was quite remarkable how many of the scientists I talked to had some sort of religion. But I think there are two sorts of religious scientists. There are the deists and the theists. The deists are those who say, for example, you know, one of the big is, well, where did all of this stuff come from? What created all of this, you know, this table, this dice, the pendulum? Where did it all come from? And many scientists, we just do not know the answer to that. We don't know the answer to that. And some people will call the answer to that unknown. Look, I don't know the answer, and I'm just going to call that the God which created it. And we might find out more about what that God is, but that's what I'm calling God. And now I'm a scientist, and I do my science, and I don't think this thing acts in the world and changes it. So those are the deists. And I think probably Einstein, when he talks about God, is thinking more about that kind of idea of the unknown. But Polkinghorne is slightly more interesting because he's a theist. These are people who believe that their God actually acts in the world and transforms it, changes it, and that maybe you can actually help influence this God to change the world. So I was interested to talk to him about, well, okay, you're a scientist. How is your science actually working to actually have some sort of action in the world? And I wondered, as a quantum physicist, whether he might see that sort of unknown of quantum physics as a window of opportunity for an external force to actually make some action. Because, you know, if actually within the system we can never know where the electron is going to be, then maybe that's an opportunity for something external to be going, okay, well, now I'm going to put the electron there. And because chaos theory actually means that a very small change can have a big outcome, maybe actually where the electron will go can cause quite a big effect on the outcome. But Polkinghorne didn't go for quantum physics. He said, well, no, that still depends on an observer. So you have to observe the setting in order for the wave function to collapse. And he didn't believe that sort of God would be waiting for, his God would be waiting for observation to happen. And he actually chose chaos theory as his little kind of window of the unknown for his God to act in the world. So he believes that as humans we can never know how a system is completely set up, so there'll always kind of be decimal places which are unknown, where you can actually start to tinker with things and actually have an effect on the system, and you don't have to affect things like conservation of energy, that it's still possible to move the system, conserve energy. And he believed that that might be a place for his God to act in the world. Interestingly, this is not a new idea. Newton himself, also a very religious scientist, also believed that within the decimals that his God could actually change and affect the world. And he had a big fight with Leibniz. He had many fights with Leibniz over the calculus and things like that. But one of his fights, Leibniz said, well, I don't get it. Why wouldn't God set up the system to be sort of perfect in the first go? I mean, why does he need to sort of interact, or he or she or it need to interact with the thing? So it's interesting that it's not a kind of new idea to use the ideas of the small changes can have big effects. But for me, one of the interesting things is that quantum physics actually might give us an answer to one of these big unknowns, which I think is responsible for many people being religious, which is, well, where did all of this stuff come from? I mean, for example, my pot of uranium, where did that come from? Well, I bought it on Amazon, actually. It's amazing. You know, you can write reviews underneath. So some of the reviews are amazing. Like, one guy said, so glad I don't have to buy this from Libyans in parking lots of the Mall anymore. So, there was one who was complaining and said, I've had this for 4 billion years and it's half full. Already you get the half-life joke. So, but no, where did this come from? Okay, well, it came from a mine, ultimately. Somebody dug it. But okay, but where did the uranium come from in the mine? Well, we now know that uranium had to be created inside a supernova, crushing all of these particles together to fuse them into this very heavy atom. But then where did all of those electrons and the protons and the neutrons come, which slammed together? Well, you know, if you work it back, then you're back to the Big Bang, and you're like, oh yeah, so where did all of these particles come from? Well, it's possible that quantum physics might have an answer, because Heisenberg's uncertainty principle applies to different sorts of measurements. I've told you the one about position and momentum, but there are other things which are bound together in a kind of uncertainty principle. And the other two that are interesting in this case are energy and time. So it means actually that it's not possible to have a true vacuum, because remember, energy E equals mc squared, so energy is actually equivalent to mass. So if you actually narrow the window of time, it means there's an uncertainty in the energy because of this uncertainty principle. So it means that you can never have a region of space which is truly a vacuum, because in each very small window of time, that can't be set to zero, the energy, because there has to be an uncertainty there. So sometimes the energy can have a positive value, which can give rise to particles. So it's a little bit like thinking of the equation 0 equals 1 plus minus 1. So the 0 sort of suddenly turns into a particle, which very often just annihilate each other, and it goes back to the 0 state. But sometimes those can separate, and so you can get something out of nothing. Actually, this is at the heart of Hawking's discovery of radiation from a black hole. That actually on the event horizon of a black hole, you can get these quantum fluctuations happening, such that a particle forms on one side and an antiparticle on the other, and then they can't actually get to each other. Particle emits, the antiparticle starts to degrade the black hole, and it's a way that black holes can actually sort of start to sort of seep away. The rate is so small that at the moment we haven't observed it, which is why he hasn't won the Nobel Prize yet, but once there's an observation made of it, that will probably follow. So it's the same principle about why black holes are actually radiating. But you know, actually, if you think about it, okay, still, empty space isn't nothing. That's really nothing. Where did the empty space come from? It's a 3-dimensional space, or maybe an 11-dimensional space. So where did that come from? You've still got to answer that. Once you've got space, it might have fluctuations which give rise to particles. But now sort of our ideas of quantum gravity are beginning to give us even the possibility that fluctuations in quantum gravity can give us space out of genuinely nothing. So it's interesting that quantum physics might be a way to answer one of the really big unknowns, which causes a lot of people, I think, to have to create. So that was a little exploration into the edges of the unknown of quantum physics. So I'll give you a little busy guided tour. How are we doing? We've got 10 minutes left. Good. Okay. We've got to do 5 great unknowns in 10 minutes. Oh my God. Wow. That's a challenge. So one of the things I was intrigued in is, okay, what is the uranium made out of? Because uranium. Okay, so I mentioned electrons, protons, and neutrons. We believe are indivisible, but what about the protons and neutrons? So, you know, at one point we thought atoms were kind of indivisible, but then they pulled apart into these and neutrons, and then the protons and neutrons we discovered are not indivisible. They pulled apart, and we now know there are quarks at the heart of those, and that we think is the kind of the indivisible bits which build all of matter. But that's our generation, and as my book sort of illustrates, I go through, you know, the history of science, and we just see each new generation has a different story about the next layer down. So how can I ever know actually that I've hit the last layer? Well, how do I know? The quarks will come apart into something else, and those will come apart into something else. So can I ever know that I've hit the last layer? Is that actually an unknown? Because you know, maybe it's turtles all the way down. You know, so the unknown are the very small and also the very big. What about the universe? Is the universe infinite? Is that something we could ever know? We could explore the universe, but actually Einstein has given us a kind of a limit on can actually see about our universe. So let me take it into here. There's a kind of cosmic horizon surrounding us. Beyond we cannot actually know anything, because information travels at the speed of light. The universe has been going 13.8 billion years. That means actually we only have received a finite amount of information coming into us. That bubble, beyond that, no information could have reached us. So we can't know anything about beyond that. Now that bubble is growing, so we're sort of seeing more and more, but we'll only ever see a finite bit, so how can we ever know it's infinite? But not only that, the universe is accelerating in its expansion. It's actually pushing things over our cosmic horizons. So as time goes on, we're actually seeing less. We're going to get to a point where actually all the galaxies are pushed over the horizon. We'll come back to a very ancient kind of view of our universe, that we are just one galaxy in a massive void. So I think that's a point of challenge. Could we ever know that the universe is infinite, if it is? So that was the very big. I think one of the other great unknowns is time. The question of what happened before the big. Could we ever? It's a singularity. We can't know. The maths denies us access to time before the Big Bang. Will time go on? It turns out, it seems like time is actually finite. Now, I used to with the belief that you can't before the Big Bang, but there are kind of rumble cosmological corridors that actually maybe we can answer that one. We can talk about what happened before the Big Bang. Time is still one of the big mysteries. The last which I talk about is my own area of mathematics, which is actually partly an inspiration for this whole book, because in my area of mathematics, we actually have a proof of the limitations of our tools. It's something called Gödel's incompleteness theorem, which says that there are true statements about mathematics which you cannot prove are true within your system of mathematics. So actually we've been able to prove there are things which are true which we cannot prove are true. Which is amazing. So, so that was partly my inspiration. But I think the penultimate edge, well, I've got 5 minutes to tell you about this, which I think is a really interesting one, because it goes to the heart of who we are. And this is the question of the hard problem of consciousness. What is it that makes us have a sense of ourselves inside our bodies? That's something we can ever know. And actually, the object I took, I think the real challenge, Wittgenstein kind of summed it up. Consciousness is a little bit like we've all this box, and inside it there's something we've all called a beetle. But nobody can look at anybody else's box, and so we don't know whether your beetle is anything like my beetle. And this is a real challenge. You're all conscious, I hope. Some of you are looking a little bit dazed by now. But I assume you're all conscious. This kind of idea of homogeneity. You're all quite like me, so I assume your consciousness is quite like mine. But how can I actually know that? Now, how can I actually be sure that tonight you haven't all sent your avatars along to this lecture, and in fact you're all at home sort of catching up on Poldark or something, and in fact there isn't, doing a very good impression of a conscious being, but how can I actually that there's anything going on? And I think this is the real challenge of actually understanding firstly what it is. What is it about putting electrons and protons and neutrons together which gives a sense of self? Then secondly, how can I ever know that somebody else has that? As I said, I think you're fairly similar to me, but what about my iPhone? Where is my iPhone? So the object I took with me on my journey to the edge of consciousness was an app that I downloaded on my iPhone, and what it does is a chatbot app. So I talk to it, and it talks back to me, and kind of tries to be human. It's trying to pass the Turing test. And maybe it is. Maybe there's somebody on the other end of the line actually typing these things in, and that's the kind of challenge. How can I know conscious or not? Remember that granny who was always put very polite words in Google because she assumed that somebody was actually answering these questions? She said, please could you tell me the... but I think the real challenge of consciousness, and the challenge at the heart of this edge, is actually, well, how can I ever know that this has become conscious?